Okay, thank you very much everyone for coming. So it's an honor for me to present Roland back on. He's going to give the talk today. He's visiting at the ISC this whole week. So I myself am new here. Probably a lot of people don't know. I've just recently arrived as a postdoc here. Well, Roland is the PI of MUSE, the integral field, the wide field integral field observer instrument on the VLT, and so he's been involved with integral field spectroscopy from the mid 80s. In fact, he even coined the term integral field spectroscopy, and so yeah, he's been involved with many instruments ever since. Tiger on the CFHD, and then Oasis, and then Sauron, and finally which all culminated in MUSE, and many new instruments in the future. So he's also received many prestigious awards. Just this year he received a prize from the Nobel Academy of Physics, and last year from the French Academy of Sciences. So thank you very much, Roland, and can you please
Thank you.
start?
Not the prize, just an award. Thank you very much. So it's a pleasure to be here. I would like to thank Johan and Mohammed to host me here, and everyone. And I see that you have really a small room here. But okay, I will try to show a bit what we've been doing with MUSE in the field of galaxy at high redshift, and I will present MUSE in short a bit to show what the instrument looks like, and then I will spend most of my time on speaking about the MUSE deep field and what we've learned from it, and a few conclusions and next steps. So what could be the next step? There's a lot of things that I will not present, which are part of the guaranteed time observing we are doing with the consortium of MUSE. And if you are interested, we can discuss that further while I'm here. But so it's only a small part. Okay, so MUSE. So short, MUSE is a large field integrative spectroscope instrument that was built for the VLT as a second generation instrument. And it covers the spectral domain of the visible with a medium spectral resolution and a field of view of 1 arc-minute square, a sample at 0.2 arc-second. And there is a small narrow field mode. I will come to that later. And it has been recently coupled with the ESO facility. I will show a few spectacular images on that. And one of the characteristics of MUSE is its excellent throughput. So it's 40% end-to-end, including everything, which I think was one of the greatest achievements of the instrument, which was really important to do this deep field science, but also many others. And so the consortium is a consortium of 7 institutes, including ESO. And you see the timeline, so that's really long operation, starting 2001 for the call for ID, and then the first flight was in 2014, so nearly 30 years of development. The cost of the instrument itself was 7 million hardware, total of 20 million. That does not include the adaptive optics facility, which is almost the same amount in total. And for the work we did, we received 250 nights of guaranteed time that we have now nearly consumed 2/3, a bit more. And we have assembled a big science team of 80 scientists that is doing things with this GTO. So how it looks like. So that's MUSE. So when we enter the instrument, we first see the optical derotator to correct for the Earth's rotation. And then we have a set of 2 mirrors that will produce that enlarger and go to a first slicing unit, which will slice the field in 24 identical fields, rectangular. So we are going to follow one and to see what happens. So now there is a number of mirrors and lenses which will send the light to the 24 identical integral field spectrograph by themselves. Okay? So in these, what we see the first and maybe the most important part is the slicer, which really slice this field in 96 small parts, which are sent to a spectrograph. And so all this rearrangement allow to match the full field of view into the 24 EFU and the 24 detector. Okay? And this is here which was optimized in terms of throughput and everything. Now you put some mechanics around and you're done, so that's really quick. So recently, MUSE was coupled, it was foreseen from the start with the adaptive optics facility of the VLT. So the VLT for the first time was one of the unit, the UT4, was transformed as an adaptive optics telescope, where the secondary has been replaced with a big deformable mirror of 1,000 actuators. And then you have 4 laser stars to be able to correct for the turbulence layer. So there is 2 modes. The first mode is a ground layer adaptive optics. So this is a mode that intends to improve the spatial resolution. It doesn't allow to go to the diffraction limit, but the beauty is that it works on the full field of view. It has absolutely no impact in the throughput of the instrument. So the throughput is as it is. And then you go from what you can see here is, let's say, relatively poor seeing, so let's say 1 arc second, and then you transfer to 0.8 or 0.6. So it doesn't look like a big difference, but usually it makes a difference between really good observation and really poor observation. You can really see here that a few stars here in the outskirts of this planetary nebulae don't show very well here, and here you can see. So you just go deeper, and then you improve it. And the beautiful thing that it works mostly all time, and that was really one of the achievements of ESO engineer, to make this working all time on a regular, whatever the thing. So now it's in full operation, and if you are going to ask for MUSE time, you will use this mode. The second mode is the now-field mode, much more difficult. Here the idea is that to correct not only the ground layers, which is more or less the first kilometer of the turbulence, but the full turbulence. And then you can only do that on a small field of view, okay? You need some relatively bright target and so on to perform tip correction and so on. But when it works, it's very spectacular. So you can see here that's in the wide field mode a globular cluster observed. So that's the central part which is seen by MUSE now field mode. So 7 by 7 arc second, and you see. And when you make the now field mode, you can see really the difference. And difference is very speak by itself, but it's even better than the HST ACS image. Okay? You can probably have seen this image of Neptune, which is where you see between the open loop and the closed loop the difference, and also it looks very comparable to, and even better to the HST image. And that's a double nuclei galaxy where you can see. So it works very well. And I just want to mention one of the first papers that was published on the now field mode was done by Johan just recently, and where he will explain it to you probably, but that's where he can resolve at this very good spatial resolution the nuclei of the galaxy with a counter-rotating decoupled core and many other features. So to understand the physics of this complex object, of course, this is very important. Okay, so now I come to the question of deep fields and high redshift. So there are many challenges for us to understand in the galaxy formation and evolution, and one of them is really to get better constraint on the low mass galaxies, because they are the ones that dominate the mass budget of the universe, and they are the ones which are the most difficult to understand. Of course, we get a lot of very interesting data of the very big galaxies, like this one in Central Cluster, but really what we want to see is the small galaxy, the progenitor of our normal galaxy that at that time assembled to form what we know now. The second aspect, which is even more important, is to understand the interaction of the galaxy with their environment. We have, of course, a good idea of this type of interaction. It's a very complex system of feedback, the gas getting in, forming stars, stop the star formation, winds. All these processes go on together in a way that we don't really understand very well. We can simulate them, but we definitely need much more information about this process at high redshift. And these are the two, so the low mass and this interaction of galaxy with our environment, where we try to get some new information with MUSE. And so from the start, when we built the MUSE, after the successful story of building integral field spectroscopy with, as Mohammed mentioned, Tiger, but also Soron, which was operated here at the William Herschel, very successful instrument on nearby on nearby galaxies. Well, the idea was to try to get really at high redshift, and for that, the idea from the start was to do 3D deep field, say, to look to deep field with an EFU. And so that was in the original plan, to have a few deep field at various size, and we did it. So that sometimes the plan you develop for an instrument are not done 10 years after, but sometimes it works. And just to remind you how you can get information on faint distant galaxies, the various ways, and the obvious way are to go to broadband deep imaging, like HST has very successfully did. You have the advantage to have a very large field of view. You can go to very deep observation and go to very faint source, but you have some limited physical information because you don't have access to the spectral information. You can, on the other hand, do multi-object spectroscopy, and this is what mostly was done before MUSE. Then it gives you really detailed physical information, but it's still a limited multiplex. It's limited to relatively bright source, and maybe the most important point, which is that you need pre-selection. And by pre-selecting what you're going to observe, at the end you maybe bias the question. And that, I think, one of things very important. On the EFU deep spectroscopy, you can go to very faint, you don't have the question, but you have a strong field of view. Clear. So these three aspects are probably complementary. Okay, so what we did was to go to the Hubble Ultra Deep Field. It's the deepest image ever observed, of course. So it's a must-do for any instrument that wants to do faint spectroscopy. So we observed this field with various ways. So we do a MUSE wide, so it was really with the depth of 1 hour. And then we've done this MUSE deep and ultra deep. So the MUSE deep was really to cover the full ultra deep field. And one of them where we go deeper. And then we recently just finished the MUSE extreme deep exposure, where the goal was to go beyond 100 hours of depth. And, so not yet result, but I will show what we've done. Okay, so that was the observation of the of the UDF with 3 individual fields plus one other one where we went deeper. Just to remind, I think it's important that was done with relatively good things, so better than 0.8, because I think we thought it was important, and it is. But now it was before EO, and now with EO we can do that with increased spatial resolution and much faster, because you don't have to wait that the thing is good. And that's, I think, one thing very important. So that's how it looks like, the white light image of the mosaic, the night field. And you have one field of view here, the UDF, with a depth of 30 hours. Okay. So, yeah, so workflow, that's the usual way. You do the data reduction, then you have to detect the source in this big data cube, then you have to extract the spectra, do the redshift measurement, find some emission line, and then get the category. So something which looks like the normal way when you do that. But it's the first time we really do that on 3D spectroscopy, on a data cube. In fact, there's no real tool. So it took some time because we had to develop everything to get there. And it's not so easy. Then I showed just an example of, that's first, the data reduction improvements. So that's what gives you the pipeline. That's one field of view, highly stretched to see how bad it can be, but was still very good. And you see the residual of the fact that you have slice the image in many subfields. So it is removed, but up only to some level. And then we have on the red part with all the OH line some residual to the sky subtraction, which is always difficult. So by working hard on the same field, we achieved something which is now, I think, very good by doing mostly developing self-calibration, super flat field, all this sort of thing. It took some time to get there. So when you look to a data cube and you look to objects, I think it's a very interesting way and a bit addictive. You spend your time to finding targets. It's great. And I just want to show you two examples to show how interesting and the complexity of it. So that's a very nice galaxy, beautiful spectra. So let's zoom on it and say, oh, nice. So that's probably H2 region, all of them. And okay, not very interesting. You probably will never put a slit there or mask, but you should, because it's a beautiful Lyman-alpha emitter. So you can see the asymmetric shape of the line and so on. So really, by looking to object from the continuum, you get just a biased view. So what you are going to select and to look. So maybe the most interesting object, as I say, is the one you will never put a slit. But let's look to another one. So that's the HST image. You see a nice galaxy there. You see in the white light MUSE. Okay. So let's look to that. So it's a bit noisy, but it's fainter. It's 26. You see here the nice emission line. It's asymmetric, and it's a redshift 3.3 Lyman-alpha emitter. Nice. Okay. Then you can even compute the flux of it. You can even compute the equivalent width because you get a continuum light here from the HST image, and then you can derive a number of interesting parameters. But let's just do the narrowband image reconstruct from the Lyman-alpha line. Then you say, no, it's not there. It's quite extended. It's completely outside the object. And let's compute the flux again. Beautiful Lyman-alpha line, much better than here. It's clearly a Lyman-alpha blob. You see it very well. And then, of course, the flux, you missed a large fraction of the flux, of course. And, of course, the measure of the equivalent width is completely wrong because it's not connected to this object. So that's all what you do when you dig with this big data cube. You find a lot of complexity, and you have to remind that if you do multi-object spectroscopy, you will never see that. So that's the achieved sensitivity of the data and what we get. So that's the state of the art prior to MUSE of this type of observation. This is the most emblematic field, and in 10 years or maybe a bit more, the number of good spectroscopic redshift known in this field is relatively small. And more or less the magnitude of them are limited to 25, and the redshift mostly to 3. And this is because it's just very difficult. Most of the galaxies are very hard, very faint, and so on. When we did MUSE, you probably will see the difference. You get a factor 10 more objects. And not only you get a factor 10 of objects, but you get a full redshift distribution up to the limit of MUSE, redshift 6.7. Okay, so you really start to probe the high redshift. But you also get magnitude to up the limit of Hubble, many. So just to give you a glimpse of the quality of the spectra provided in this field, so that's for nearby source, you look for the oxygen 2 emitter, well resolved, magnesium 2, carbon 3, that's a big AGN. And then you have all sorts of Lyman-alpha emitters, big, small, extended, not extended, huge collection. You can do quite a number of interesting things with them. Look, so this is the HST image, and this is a narrow band. You already feel the difference, the fact that they probably are diffuse and so on. That's a completeness. So in this field, we achieved a completeness of 50%, up to a magnitude 25 or 26, depending on the depth. But what is interesting is because of the Lyman-alpha line, in fact, even the very faint object up to magnitude 29, we get 20% of them you will measure the redshift. So that's, I think, very important also to notice. So even for the very faint object, if you are interested and if you are ready to spend some telescope time, you get a good chance to get a spectrum. Okay, so from this, you can get a lot of data that I won't detail here, it's too short. But so we publish a first set of paper on the series in AAR at the end of 2017. I will just sketch a few, which I think is interesting. So the luminosity function of Lyman-alpha is of course very interesting because we want to probe the faint end. That was the original game. Okay, and the idea is that can we see the impact of at redshift 6 of the start of the end of the reionization or not? So we've been able to cover compared to the previous work really to the faint end, but we've not been able today to really get very good measurement. We still have to do a bit more work to probe the end of the reionization and to see a difference here in the redshift evolution of the luminosity function. So it's work in progress. The surprise also is that we found a number of objects that were not in the HST catalog. Remember that these fields are the deepest image ever obtained. Okay, they go to magnitudes of 29, 30. And was not completely clear that we will get new objects. But that's clear that we get quite a number of objects that you cannot see in the HST. Some were just missed by the sextractor process. Okay, but half of them are really new. And I will just show an example. So this is one MUSE spectra. You see the Lyman-alpha line, zoom, that's a narrow band. Here you see clearly the narrow band. And this is the HST image in these two bands. and let's zoom on it. Okay, so you see something, maybe, probably, and but it's damn faint. And that's a redshift 6.2. And there is a few where you really don't see anything, so but you still see the line very well. Okay. So the interesting thing is that these objects are there, even in the HST image. Now we do the stacking because we have a lot of this object, and by doing the stacking, you recover. So you stack by according to the filter, and you recover the break. So that's the stacking of all the HST, of all the Lyman-alpha emitter, and so the data is really and that's really nice to see, a nice confirmation. So we can really get a dig to very faint objects. So faint that most are upper limit, but in average, you see we really probe here very faint objects, which was the goal. And just recently, we've been able to use the stacking also and in IRAC, and to show that we can get some information with H-alpha. Of course, this sort of object would be, of course, keen to see with the James Webb when the James Webb will fly. And we can provide target for the James Webb to understand these high star-forming galaxies. The other thing is that Lyman-alpha is nice, but it's only one line, and to get physical information, and it's a difficult line because of the scattering and so on, and so get other line is nice. So that's some work that was previously done by Shapley by stacking a lot of Lyman-alpha emitters, but mostly bright, and then we start to do the same but probing this magnitude range, so going fainter again. And can we see some difference? And so by stacking the bright or the massive one, you can get a very high signal to noise, and you can get a number of very interesting lines, like the carbon, silicium, carbon-4, and so on. And you can also do the same on the faint one, or the low mass object. Okay? And we actually see a difference. So that's in the faint one. You can see that the carbon-4 is quite important, while you almost don't see it very well on the massive galaxy. But on the helium and the oxygen-3, it's almost the same. So that's already a signature of the spectral property of this object, and this is what we are going to study. So, okay, so the circumgalactic medium. So circumgalactic medium has been, of course, one of the major points, and this is currently under study. And the way we usually do is to get absorption line study, where you can probe the content of the neutral gas along the line of sight between a quasar and ourselves. But there's not much quasar, and they give you one dimension, of course, information. Okay? There have been some attempts to do with galaxies and so on to get more information, but of course we would like to probe really more the circumgalactic medium as a wall. Can we see it in emission? And that's what we try. And with MUSE, because we go so faint, it is possible to probe the CGM. And so we find that around Lyman-alpha emitter, we can probe the content of the CGM up to large distance. So this is a comparison of, let's say, the size of the continuum, which is mostly, in most cases, unresolved, and the size of the Lyman-alpha emission. Okay. And that's, I think, a very interesting. And the conclusion of this work did show that these faint diffuse emission around Lyman-alpha emitters are almost ubiquitous. So we see all of them. And that we 80% exactly of our samples. And that's the size of the low surface brightness emission in Lyman-alpha extend to a factor 10 larger than the stellar continuum. So we're really starting to probe scale which are comparable to the CGM size. And this is really important because we have for the first time to be able to investigate the shape, the content, the physical content of the CGM in a different and complementary way than just the line of sight of quasars. And also most importantly, that a large fraction of the flux is in this big halo. It's fairly extended, and at the end you can have up to 70% of the flux which is in the halo. So if you compute the Lyman-alpha flux, for example, for the luminosity function, just with a single aperture, you miss a large fraction of the flux. And so from this, we would like to understand the process of this Lyman-alpha emission, either scattering, co-stream, and whatsoever. Very complex process, but we start to be both in terms of the observation and the simulation, starting to understand these. So that's, I think, important. And so there's work in progress to get the spectral information of it. And there's further progress we are doing with Mohammed on that. It's such ubiquitous that if you can ask yourself how many of the Lyman-alpha halo are there. And if we look to any portion of the sky, what is the chance that we cross one of them? And the chance is 100%. So the sky is fully covered by Lyman-alpha. And this is what we compute by stacking, so trying to go deeper in the surface brightness. And from that, we can already cover close to 100% of the sky. So if you look to this UDF image, well known, but now you take your Google specially adapted for Lyman-alpha, this is what you'll see. So it's this we really start to see all of them, and I think it's really what we were looking for. And we can also compute this incidence rate of the Lyman-alpha emission, and the fact that it compares to the high Coulomb density of absorbers seems to show, it's not a proof, but seems to show that most of the neutral gas, we're starting to look to it. And I'm here also to work with Mohammed on this new way to detect blindly this faint diffusion, work that we started in Lyon a few years ago, and is now almost done. And I think it's very exciting because at the end we want to use this advanced tool to detect the gas, not only the CGM, but ultimately up to the AGM to really look to the cosmic wave in emission. And this is the work currently in process. So we currently probe size of 70 kiloparsec, but can expect to go even further. And for that, we have started to do the MUSE extreme deep field, the MXDF, that was we just finished of the observation in January. And this is one field in this UDF that we try to push to more than 100 hours. And in fact, in a semester, we've been able to push it to 150 hours with a very good spatial resolution. So this is the scene distribution. So the gray one is the UDF 10, the best one we had, where we get all these results. It was only 30 hours. Now we have 150 hours of this, and this is really given by the adaptive optics GLAO system. You just go and you just get a better scene. And in 6 months, it's possible to achieve a fantastic depth with a good spatial resolution. So we look forward to look to this data set. And this is how it looks like, because we've done, it's like a bit like cheese or cake. It's going to be the deepest observation ever made, for sure. Okay, so to conclude, I think we've been successful with MUSE to get access of the low mass star-forming galaxy at high redshift. We're just starting to understand what we see and to model it, but I think there's a lot of data. And we also get this fantastic information of the CGM at redshift larger than 3, and many other results that I don't have time to explain. Yeah, so what's next? MUSE is highly oversubscribed. I think mostly a factor 10. So it's hard to get time. And it's not going to change because MUSE is really has a wide physical and astrophysical application. It goes to stars, stellar cluster, and many things. Okay, and it's unique. So the idea came to build another one, but a bit different, on another UT, to have 2 instead of 1. And that's blue MUSE. So the blue MUSE will cover the blue spectral range. So from the atmospheric cutoff to this wavelength range. And this is a nice part because there's no OH line, so it's an easy part, and you still get a good transmission here in parallel up to that wavelength. And the idea is to do as good as MUSE did. MUSE has the best throughput of any of the spectrograph at the VLT. And this is the throughput of MUSE, okay, compared to the other spectrograph. And I think, applying the same recipe, optimization, all the work, the hard work we did, we should be able to do almost as good as MUSE. And what we want to do is to double the spectral resolution, because currently it's one of the limitations for stellar science, but also maybe for cosmology. In some cases, you need a better spectral resolution, and we think we can do to double the spectral resolution with respect to MUSE. And the idea is to double the field of view as well, if it's feasible. And so here we will double the surface, 1.4, 1.4 is probably the maximum we can do on the VLT platform. We will do the sampling of 0.3 arcseconds because we don't need AO at this wavelength range, it doesn't work. And then by doubling the field of view, you double the discovery space. And MUSE has a very large discovery space, and that's what we want to do. And so for doing that, we will use new technology like curve detector that allow to simplify the optical systems and get an excellent throughput. And science case could be the same as MUSE, but it could be a lot of different things, and we are working on that. On our galaxy and the local group, you can do massive stars, ultra-faint dwarf, nearby galaxy, you can go to ISM, X2 region, extreme starburst, low surface brightness galaxy. And even on the distant universe, you will, for example, probe the Lyman-alpha line from a redshift of 1.9 at a time where the cosmic star formation peak, and you expect a lot of things to happen. On the other case is that because of the redshift dimming, we will be able to probe much better than we do now, let's say easier, all the CGM, the faint diffuse emission, and including the cosmic web with this sort of instrument. If you are interested in deep field, we have this one EVAS symposium in Lyon in June. Please come. There is good food also in Lyon. and I just end by showing a few results from MUSE. Thank you.
Very much for the interesting talk. We have time for questions, but please wait for the microphone so people following the streaming can follow the discussion.
Thank you. The result that you showed that most, 80% of Lyman-alpha emitters show standard emission, that's interesting. Some was expected, so I would say. But what would be your guess for the Lyman-alpha emitters which also have continuum? I mean, would you expect to have such a high number of standard emission in those, the thing you are going to sample now?
Yeah.
So because these are more galaxy-like things, in
Yeah.
which the standard emission is more related to the galaxy itself and probably less related to the cosmic wave or whatever.
Yeah, so currently, so for example, we expect probably 100%, just a problem of detection for the galaxy don't show. But we have some galaxy that we will show the extended emission and probably not the galaxy itself, or very faint. So we are going to probe that. So I'm not sure I get completely your question, but
the pure Lyman-alpha emitters, which are basically what you have been sampling with
yes.
MUSE now,
Yeah.
so you have something which is a block which emits in Lyman-alpha,
Yeah.
an extended emission, which you say that is in 80% of the cases,
Yeah.
you have an extended emission.
Yeah.
That's right.
Yeah.
So now you are going to go for Lyman-alpha emitters, which also have continuum, which are other sort of things, right?
Yeah.
So in this case, do you expect also that in 80% of them, you are going to have extended Lyman-alpha, because the origin for this extended Lyman-alpha may be
Yeah.
different in these cases?
Yeah, so we are going to probe this regime also for the absorbers, which are quite interesting, more massive objects also. But I think, and there was some previous work by Steiner, if I remember, by Stacky, that show even the absorber shows this emission. So the DS emission is just showing by the various process, probably more than one process altogether, to produce this emission, which can do just to scattering, but also maybe to cooling. And for the objects that don't show at all the galaxy, then we probably have to look to other processes like really cooling of this.
More questions?
So it's really breathtaking set of results. So it's really amazing. So this is a very simple question about how do you deal with the change in spatial resolution with wavelength. So you told us that you have PSF that differ in the blue and the red.
Yeah.
So how do you deal with that when you extract spectra?
So we have a model of the PSF. So without EO, it's relatively well known, and you can figure out easily. The change is not so big. With EO, of course, the impact of the EO will improve better in the red. But with GLO, as you correct, only the ground layer, you still get some correction in the blue. Okay? So we just model it. And then when we extract, we just adapt the kernel to the size of the PSF. It's just that recently, with the EO, sometimes you really need the information. And so we have developed a model to get the PSF information directly from the wavefront sensing telemetry. And it works fine. So because you get all this information, real-time information about the atmosphere, you can infer the PSF with a good precision. It's going to be something important, especially for future small instruments like Harmony, for example. You are part of Harmony, so you know that. So the field of view is very small, and getting, except if you have a star into it, getting a PSF is critical for the science. And there is a good hope that we can reconstruct the PSF from the telemetry.
was wondering if you could comment on any results you have obtained looking at massive galaxies at high redshift. Looking at the stellar continuum
Yeah,
for high redshift galaxies.
yeah. By high redshift, you mean
Yeah, I'm
six,
talking no, not 6.
okay.
No, I'm talking 1, 2, 3.
Yeah. So here, of course, in the deep field and so on, the field is relatively small, so the number of very massive objects is relatively small. So we have a few that are interesting in themselves, but I don't think maybe it's where MUSE will do the best, because I think with multi-object you can throw much larger sample and getting more information. So we didn't focus too much on it, but we have a few, and we have looked to that. We have looked to AGN object, or let's say very massive galaxy. There's a complete thing we've done, which is different, is we have looked also to the frontier fields, so the lensing cluster. And of course in the lensing cluster, you get both the population of the massive galaxy, the forefront, but you get also all the enhanced emitter. And that's a complete different science we've done, which I didn't discuss that here, but we get MUSE is fantastic because you get a lot of redshift at the same time. You can really probe the content of the dark matter to very accurate detail. Even that we can go up to subscale of the dark matter distribution, because we get enough constraint to constrain the model.
More questions?
Hi. Have you tried to measure any kinematics or masses from this extended Lyman-alpha emission? Because, I mean, in principle, it looks like that you could make something, no? Because they are so extended that maybe looking at the edges or so, you can get some hints of the amount of mass that is there.
Yeah, so we are starting. This is really fun, so it's difficult. So we're starting to that. The point with Lyman-alpha, it's resonance scattering, so it's not completely trivial to derive from the line kinematic information. Okay? So I think you have to go to the simulation and so on. So you clearly see difference in the spectral shape changing if you look to the CGM, REA, okay? But getting what exactly means in terms of the physics or eventually the kinematics is somewhat difficult. So I think it's really a challenge for people doing the simulation. But I think we start to accumulate a lot of this data, and probably then we can decouple the inherent complexity of the Lyman-alpha line if we get a sample large enough.
Can you tell us a little bit about this new Blue MUSE? How is the status of the project? Is approved by ESO? When do you expect to?
Yeah, so Blue MUSE is just a funny idea I had some year or two ago, looking to the success of MUSE and maybe also the idea to move it to a bit to different way. And so it was proposed to ESO, and the status that the ESO will decide on what could be the third generation VLT instrument next summer, or after the next summer, and then will be a normal process. So if we go, so we have started to assemble a consortium and see how much it will cost, what are the difficulties and so on. Yeah, it was well received, because everyone sees the MUSE success. Everyone also sees that the risk is very small, and that the European community is ready to go. So this is one of the rare instruments that should provide papers at the first minute it is on the telescope, which is important. Also, by going to the blue, when most of the other instruments like the ELT, James Webb, other are moving to the infrared. The blue is a domain where there is very important to keep, and it's really optimum. And I personally think we need absolutely to develop that. We cannot gamble everything to the James Webb, which will be difficult to get time. Even the LT, which always will be small field. And there is a space of discovery space here, which is
Well, yes, some propaganda and some a question. Here at the GTC, we have developed a survey named SHARP, which is a sort of a spectrophotometry, which not so broadband filters, but relatively narrow, and a number of them.
Mm-hmm.
So with that, we have a sort of, poor spectra, and with this data, which is on the Hubble Deep field, right? We have also been able to detect sources that were not detected, not seen in the HST. Basically, because we have been looking for emission line targets, and for that, this sort of technique is far more powerful, as you have shown.
Yeah.
So this is the comment, some propaganda for this SHARP
Yes,
survey that
yes,
we have at
right.
the GTC, but also because it's this on the same target, on the same field that you have been working with.
Yeah.
I was wondering how possible would be to have some sort of collaboration. In particular, you have shown a number of data which are, they're very, I suppose all of us will want to play with them too, right? And then because we already have a large catalog based on this survey, I was wondering if it would be possible to look for some of these targets already detected in your field, in your catalog, in your survey, whatever.
Mm-hmm.
I mean, how possible would that be?
Sure, you're welcome. I think there's, you see, that I think the decoy space is large, so I think there's plenty of space, and it's very nice. So I think, yeah, let's discuss that and see. It's here. I think the focus with MUSE is the extreme depth on relatively small field. So I think it goes this way. So if you are interested to look one of this source with your facility, of course, that's very interesting. Yeah, and vice versa. There may be some possibility.
Yeah, there are already targets identified out of this survey.
Yeah.
Which can be within your field. I mean, this is your...
And MUSE is available to you. It's ESO property.
Maybe you know that we are in the process to define the new instruments for GTC. So what would be your recommendation in this MUSE-like instrument?
I think a MUSE-like instrument in the north is certainly a good idea. But I don't know, it depends on the science interest, but I think a MUSE instrument maybe, well, if you want to build a facility with AO and so on, that's very complex, very expensive and so on. But today a MUSE instrument, that's maybe blue-like or maybe average or something in between without AO, the technology exists, and the science prospects are good. So if it probably will match well the site characteristic and so on. So if you are interested, let's look to it.
Thank you.
Will not be me. I'm too old, but maybe can channel the idea.
Any last question? So if not, I think Professor Bacon is going to be here the whole week. Johan? Mohammed? Yes. So you can contact Mohammed, I guess, to contact him, or Johan? No? Okay. Mohammed. Thank you very much, and thank you very much for coming.